All right, so now let's take a look at a different problem. So this problem is on understanding the impact of cache performance on CPI. So we have computed CPI in the past for the different data paths. So now we are going to try and use that same method of computing CPI, but account for the cache performance. So the way to go about solving such problems is to first understand what is the CPI composed of. Now the CPI has several parts to it, but on average what we are asking is what is the average clock cycle that an instruction would take. So in this example, we are given that we're given some information here, so then we can compute based on this information what the CPI would be. So it's a pipeline data path, and so the CPI is going to be 1 in the ideal case. But then we need to account for the different types of hazards that we will see. So the different types of hazards are, you have to have some penalty for data hazard, some penalty for control hazard, and now we also need to have penalty for iCache miss rate and data cache misses. So and keep in mind that every instruction needs to access the instruction cache to get the instruction. So every instruction is potentially can miss the cache, right? The instruction cache. The data cache, on the other hand, is only going to be accessed by loads and stores. Okay, so these are the 4 components, and now we have to think about what are these 4 components for this given problem. So the data hazard penalty is due to the data dependencies, the read after write dependencies. And so in a pipeline data path where you are assuming full data forwarding, you have a penalty only for the load instructions that are immediately followed by a dependent instruction or followed by an immediate use. Okay, so for this problem, we are given that there are 15% of instructions are loads, and of those loads, 50% of them have this pattern where it's immediately followed by a use. So the data hazard penalty would be, I have 15% of loads, of them 50% have an immediate use, and the penalty when this happens is 1 cycle, because you need to stall the pipeline for an additional cycle. And the control hazard is going to be only for branches, so I have 20% of instructions are branches. Of those, 40% of those branches are taken. So now you need to think about what fraction of branches are going to be mispredicted, and for that you need to know what type of a branch predictor we are assuming. So the branch predictor is assuming that all the branches are not taken. So whenever a branch is taken, it would be a mispredicted branch. So 40% of the branches are mispredicted, and whenever that happens, I have to incur a 3 cycle penalty. So now finally I have to compute the instruction cache misses and data cache misses. So like I said before, every time when you execute an instruction, you have to fetch, decode, execute, mem, and write back, right? The fetch stage fetches the instruction from instruction cache. Now we are told that if there is a cache hit, it's always 1 cycle. So what that means is the fetch can finish in 1 cycle, so there is no need to add any additional penalty. But 3% of the time, you may have an instruction cache miss. And when that happens, you have to go to the main memory. So 3% of the time, that is 0.03 times, I would have to go to the main memory. And if I do go to the main memory, I have to incur this latency. Now I need to translate this latency into a memory cycle, clock cycle, so that I can plug this into my equation. So for now, I'm just going to assume it's m, and then I'm going to come back and compute what that m is going to be based on this main memory latency that is given to me. And so finally, I have the data cache miss penalty. And for that, I need to consider only the loads and stores. So which is 15% of them are loads and 20% of them are stores. And so together it's 0.35. So for 35% of instructions, I may miss the data cache 6% of the time. And when that happens, I have to go to the main memory and incur a latency of m, which I have not computed yet. Okay, let's compute the number of cycles to access the main memory. So we are given that it takes 100 nanoseconds to access the memory. Now we need to convert this into processor clock cycles. To do that, we need to look at the processor clock frequency and figure out what is the clock period, or rather clock cycle time. So the way to compute clock cycle time from a clock frequency is clock period is 1 over clock frequency, right? So clock time is 1 over clock frequency. So frequency says I can switch 500 times 10 to the power of 6 times within a second. So now if you want to compute how many seconds or how much time it will take for every cycle, you need to do 1 over that. So that's 1 divided by 500 times mega is 10 to the power of 6. So you have 1 over 10 to the power of 6, which is equal to 1000 divided by 500 nanoseconds, because nano is 10 to the power minus 9. So this equation works out. So that will be 2 nanoseconds. So therefore clock period for this particular processor is 2 nanoseconds. So if one clock takes 2 nanoseconds, then if I have 100 nanoseconds, how many clock cycles would that be? So that will be 100 divided by 100 nanoseconds divided by 2 nanoseconds. That will be 50 cycles. So the main memory latency is 50 cycles. So that's what we had used as m here. So m value is 50 cycles. So I can plug that 50 in there. So instead of m, it would be 50. And once you compute this equation, you would have figured out what your CPI value is.